Okay, but just give me a minute. We're just starting. You can post your questions in the chat if you haven't already. The turnout is again a bit low today. People are still on their Eid break. Most schools are off in Pakistan, I think, until the end of this week. So people are enjoying a whole week off, mostly. Although those of you who have Cambridge exams, that's not really the time to be wasting like that. Okay. So this is working fine. And okay, so let's get started. So we completed the concepts of our discrete random variables, including binomial distribution in the last couple of sessions. We've done some practice on our discrete random variables already. We've done some of the difficult questions from the worksheets. Now today we want to focus first of all on practicing binomial distribution. So I'll give you a quick reminder about binomial distribution. We talked about the whole logic of it, why something can be classified as a binomial distribution, and how to and why you can use a formula that use this formula that we arrived at. But now, for solving problems, what you need to remember is you need to first identify whether in a particular question you can use binomial distribution or not, or something, or if a particular situation can be formulated as a binomial distribution or not. If it can be formulated as such, you can use this formula to calculate the probabilities. Okay. Now, what you need to remember about binomial distribution is, in binomial distribution, you will be looking for probability of getting a number of successes. Okay, find the probability of the number of successes being equal. Okay, now that's one thing that you need to keep in mind. You will always be looking for the probability of a certain number of successes. But then there's some other conditions as well that need to be fulfilled for you to be able to use that formula. Okay, I'm sorry. Let me just check my connection quickly. Okay, so LAN is not connected. Okay, thank you for finding that out. Okay, I'm sorry about that. So there was some problem with my connection. Is it okay now? Yeah, okay, all right. Okay, so first of all, we need to understand when in a particular problem we can apply binomial distribution formula. So this is the formula for binomial distribution: NCR into P raised to power R into Q raised to power N minus R. Now, when we look at some past paper questions, the first thing that you always need to be able to do is you need to figure out whether in a particular situation you can use binomial distribution. Okay, it will be very rare that they would tell you in the question that you can use binomial distribution. You'll have to figure it out yourself. How would you do that? The first thing that you need to keep in mind is that you would always be looking for the probability of getting a certain number of successes. So whenever you talk about probability of getting a certain number of successes, that's a hint that you may be required to use binomial distribution. Okay, so that's the first hint and the most important hint that you would have, that you're looking for the probability of having a certain number of successes. Number of successes is the keyword that you will have in binomial distribution. Now, that's not enough. Then you have to make sure that these conditions are satisfied, and then you can use binomial distribution. What are the conditions? There should be something repeating, and the number of times that it is repeating, that should be fixed. Okay, it should not be something that goes on forever. That it should not be a repetition that just continues for however many times it can. It should be some finite number. It should be some fixed number. There should be only two possible outcomes. If there are not two outcomes, you should be able to convert them to two outcomes. You will call one of them success and the other failure. Success would generally be the outcome that you want the probability for. So whatever it is that you're looking for, that you're finding the probability for, you would say that's your success. And everything else you will classify as failure. So that's how you can convert any outcome in general to two possible outcomes. Okay. But then once you have converted them to two possible outcomes, their probabilities should remain unchanged. They should remain constant across trials. That means the first time you're repeating the first time you're doing the experiment, whatever the probability of success is, it should be the same the second time, the third time, the fourth time. It should not be changing. If the probability is changing, then that is not binomial distribution. So these conditions have to be met for something to be classified as a binomial distribution. That is important. Okay. Now that we know that these conditions have to are met, then we can use this formula to find the probability of getting a certain number of successes in a particular case. The formula is NCR into P raised to power R into Q raised to power N minus R. P represents probability of success. Q represents probability of failure. N is the number of times you're repeating something. X is the number of successes. X represents the number of successes. It's a variable. So if something is repeating 10 times, X could have a value of 0, 1, 2, all the way up to 10. You could have 0 successes, 1 success, 2 successes, 3 successes, all the way up to 10 successes. Then R is the number of successes you're looking the probability for, you're finding the probability for. So if they want you to find the probability of getting 5 successes, then you would say the value of R is equal to 5, and you would put R equal to 5 there. Okay. And then what we did was we looked at some questions on this. When you had to find the probability of getting 4 successes, we just used the formula as it is. But then if you were looking for getting the probability of if you were looking for the probability of getting less than 2 successes, in that case, we said you would have to add up these two probabilities, 0 success and 1 success. And then if we had a case like this, we wanted less than or equal to 6 successes. What we did for that was we said less than or equal to 6 successes was too many cases, 0, 1, 2, 3, 4, 5, 6. Since the total number was 10, the remaining options were fewer, like 7, 8, 9, and 10. And what we did for this was 7, 8, 9 only. What we did for that for this, therefore, was that we found the probabilities of each of these cases, subtracted them from 1, and we found that required result. Okay, so this is what we've already done in the previous class, in our first class in binomial distribution. Now, today, what we want to do is we want to do some more practice questions on this. Okay, some past paper questions, some actual questions. These are just some examples. There was also this formula that the expected value of X, the mean of X for a binomial distribution, that is given by N times P, and the variance is given by NPQ. So whenever you have a distribution that follows that is binomial distribution, then expected value and variance, they can be calculated directly using these two formulas. You don't have to use sigma xp and sigma x square p minus expected value of X whole squared that we used to do in cases of probability distribution tables. we can directly find the mean and variance using these formulas. Okay, that's what we discussed. One last thing that you also should know about binomial distribution is some notation that they use in questions sometimes. Okay, this we did not talk about earlier. We call these parameters of a binomial distribution. Parameters of a binomial distribution. Now remember what the formula looks like. The formula is NCR into P raised to power R into Q raised to power N minus R. Now, N represents the number of times you're repeating something. Okay. P represents number of successes. P represents probability of success, and Q represents probability of failure. In order to use the formula, you need these values. You need N, you need P, and you need Q. A binomial distribution is described by these things. It's described by the value of N and the probability of success. Just like if you remember, you did in paper 1, arithmetic progression, geometric progression. What was an AP described by? An AP was described by its first term, which was A, and the common difference, which was D. A GP, it was described by the first term and the common ratio, right? These were parameters of these distributions. Similarly, for a binomial distribution, in order to describe a binomial distribution, we need two things. Number one, we need the number of times you're repeating the experiment, the number of repetitions, the number of trials. That's basically the value of N. That's one parameter that you have for a binomial distribution. And the other parameter is P, which is probability of success. Now, parameter is basically something that describes a distribution. So one is number of repetitions and the other is probability of success. Why are we not using probability of failure? Because once we know the probability of success, probability of failure is just 1 minus that. So if we just know P, Q is something that we can find using that already. So we don't necessarily need to be given Q separately. Okay. So if we have the value for P, we can find Q already. These are two things that are absolutely required, absolutely needed to be able to describe a binomial distribution. So sometimes in questions you will see, they will ask you to write down the parameters of a distribution. You should remember one parameter of a binomial distribution is N and another is P. N is the number of trials, P is the probability of success. And there's a notation that they will use sometimes as well. If you have something written in this form, X, and then you have this sign, it's called tilde. You might have seen this on top of the keyboard somewhere, top left, below the escape button. It's called tilde. It's spelled like this normally. And then you have B, and then two numbers written. So let's say you have one number written that's 8 and another number written that is 0.7. If you have something written like this, you need to understand this notation as well. What does it mean? What does this notation mean? This notation means X is a variable. This sign means it follows binomial distribution. X follows binomial distribution. Why binomial? This B represents binomial. Okay. Now, what about these numbers that we have written here? It follows binomial distribution with N equal to 8 and P equal to 0.7. So whenever you have two numbers written in brackets like this, for a binomial distribution, the first number always represents N and the second number always represents P. This is a convention. You need to remember this. It's always written like this. So whenever they use this notation, you should be able to interpret what they mean by this. Okay. So in general, you can say if you have anything written like this, X follows binomial distribution, the first number represents n, the second number represents p. Okay, so these are just some terminologies that you need to be familiar with. You might find these mentioned or used in questions sometimes. Sometimes they will ask you to list down the parameters. You should know that these are the parameters. So you'll have to write down the value for n in that context, the value of p in that context. Also, they can also ask you to list down some conditions for binomial distribution. Okay, so it doesn't happen a lot in your syllabus that they ask you to, write things down like this. But this is one case where they do require you to memorize these conditions. Sometimes they will have a 2-mark question, generally, maximum 3 marks sometimes, but 2 marks more likely, in which they will ask you to list down 2 or 3 conditions for being able to use binomial distribution or for geometric distribution. So you should be able to list down these conditions. Okay, so that's why these are important to remember. And if you don't remember, then you cannot do the binomial distribution questions as well, because you would not be able to figure out if something does follow binomial or not. Okay, this is the criteria for figuring out if the binomial distribution formula is going to work in some case or not. Okay, so you need to remember these conditions for that as well. No, so it's not necessary that you write down the parameters in this format necessarily. You should be able to interpret this. So sometimes the question might use this notation. So you should be able to understand this is what it means. The first number represents n, the second number represents p. But if you're asked to write down the parameters yourself, you can just write n equal to something and p equal to something. Okay, what I'll do is I'll start with an example like this, and then we will do the questions that you guys are asking. But I'll start with a simple one first for today, and then we do the questions that you have asked. Okay, so others as well, if you've not sent your questions in yet, make sure to write them in the chat so we can discuss those questions that you found difficult from the worksheets. All right, so one of these questions that you've asked, I think it already does include this part as well. So we will just do that. Let's start with this one, question number 32. Yeah, question number 32 from the worksheet. Let's have a look at this. So you see in the first part, they ask you to write down the parameters. Okay. Question number 32 from the worksheet. Okay, now this person, Fiona, or whatever the name is, she uses her calculator to produce 12 random integers between 7 and 21 inclusive. Inclusive means 7 is also possible and 21 is also possible. Okay, and what she's doing is she's producing random integers between 7 and 21. How many integers is she producing? 12 integers. Okay, the random variable x is the number of these 12 integers which are multiples of 5. State the distribution of x and give its parameters. Now, what are the parameters? Parameters are the values of n and p. Okay, n and p. But before we can do that, in fact, we have to state the distribution of x. What's the distribution? Since we're doing binomial, you would say that it's obvious that this is going to be binomial distribution. However, how do you figure out that this is binomial distribution? How do you identify this is binomial distribution? Do you have something repeating? Do you have something repeating? You're producing integers again and again, one after the other. So you're producing 12 integers. So we do have repetition, right? Something is repeating. How many repetitions do we have? We are repeating something 12 times. So the number of times we are repeating something, that's also fixed. That's 12. Okay. All right, that was one condition. Do we have two possible outcomes? What are the outcomes? X is the number of these 12 integers, which are multiples of 5. So what is our concern here? What is it that we're looking for? We're looking for multiples of 5. So we can classify it like this. We can say success is getting a multiple of 5. That when you produce a random integer, that's a multiple of 5. That's your success. And failure would be not getting a multiple of 5, right? So we can classify it like this, that one possible outcome is getting a multiple of 5 and the other possible outcome is not getting a multiple of 5. All right. Now, so we have two possible outcomes, but are the probabilities of these outcomes going to remain constant? Are they going to change or are they going to remain constant? How do we figure that out now? Let's find the probability first of all, because we will need that as well as the probability of success. We have 7 and numbers between 7 and 21. How many numbers are these? From 7 and 20, from 7 to 21, 7, 8, 9, 10, and then 11 to 20. These are like 10 numbers, and then 21. These are 15 numbers in total. These are not 14. These are 15. Don't just do 21 minus 7. 21 minus 7 is 14. However, since both numbers are inclusive, 7 is also included and 21 is also included, we actually get one more than 14. That's 15. These are 15 numbers in total. So a number is being generated from these 15 numbers, from 7 to 21. All right. What's the probability? What's the probability that that number would be a multiple of 5? Now, out of these 15 numbers, how many are multiples of 5? Okay, let me just list down all of them for those of you who are confused why there are 15. Let's just write all of them down and see how many there are. 15, 16, 17, 18, 19, 20, 21, right? So these are 15 numbers in total. How many of them are multiples of 5? 10, 15, and 20. 3 of them are multiples of 5. What is the probability that you generate a random number and it turns out to be a multiple of 5? Probability of getting a multiple of 5 when you generate one random number. 3 are multiples of 5. Out of how many? Out of 15, the probability is 3 over 15 or 1 over 5 or 0.2. That's the probability of getting a multiple of 5. Then what's the probability of not getting a multiple of 5? It would be 1 minus 0.2, which would be 0.8. Okay. All right. Now, so I see that there's a confusion in this question. Some of you are thinking, we have 15 numbers here and they're saying 12 random integers. How do both of these things match? They are generating 12 random integers. So when you generate one integer between 7 and 21, so let's say you generate a random integer between 7 and 21, and it turns out to be 11. That's your first integer. Then you generate another integer, again from numbers between 7 and 21. Let's say it turns out to be 15. Then you generate another one. Let me ask to write it more clearly. So you generate the first one, it turns out to be 11. The second one, it turns out to be 15. The third one, it turns out to be 13. The fourth one, it turns out to be, let's say, 11 again. And then fifth one, and so on. And you generate 12 integers like this. Every single time that you are generating an integer, it is a number between 7 and 21. It's one of these 15 integers. Okay. So there are 15 possible integers that you can have. Every single time that you are generating a random integer, it has to be it has to be one of these 15 numbers. And you're doing this 12 times. You generate one integer, then another integer, then another integer. You can have repetitions as well. It is possible that all of them turn out to be 10s or all of them turn out to be 15s. That's also possible. So there are 15 total possibilities that we can have. Every time we can get a different number, and we are generating this number 12 times. Does that make sense? Yeah, okay. So one time that we generate an integer, the probability of getting a multiple of 5 is 0.2. So that's your probability of success. We can say P is equal to 0.2 and Q therefore will be 0.8. So now in the first question, they were saying, state the distribution of X. Every single time that you generate an integer, what's the probability of success? What's the probability of getting a multiple of 5? The first time you generate a random integer, the probability of getting a multiple of 5 is 0.2. The second time you generate an integer, it's again 0.2. The third time you generate another integer, it's again 0.2, because you can have the same number again as well. So for example, if you get a 10 the first time, it is possible that you generate another random integer and it again turns out to be 10. So it is it is with replacement. Sorry, it's with replacement. So the same number can come again as well. That means the probability is not changing. So it satisfies all of these conditions that we discussed. There is repetition, with the total number being fixed. There are two outcomes. And the probabilities are not changing. They're independent. Okay, so this is binomial distribution. So what do we write here? We say, number one, it is binomial distribution. This is what you actually need to write there. This is binomial distribution because it satisfies the conditions. And then you write down the value of n, how many times you're repeating something. That's 12 in this case. You're repeating the experiment 12 times. What's the probability of success? That's your second parameter. That is 0.2. And that's what they were asking for in the first part. It's binomial distribution and its parameters are n equal to 12 and p equal to 0.2. Okay, let's look at the second part now. Calculate the probability that x is between 3 and 5 inclusive. So it's either 3 or 4 or 5. Should n be 3? Why should n be 3? Where does 3 come from? N is the number of times you are repeating that experiment. So how many times are we generating the random integer? We're generating it 12 times, right? We're generating 12 integers. So n is 12.
Sir, in the question it says that the random variable x is the number of these 12 integers which are multiples of 5. So multiples of 5 are just 10, 15, and 20.
X is representing number of successes. X is representing number of successes that you can get. N represents the number of total times the experiment is repeating. Remember what these letters mean in this formula. N is the number of trials, number of times you're repeating something. X is the number of successes out of that number that you can get. So you're repeating the experiment 12 times. So numbers are being generated 12 times in total. So n is equal to 12. And then out of those 12 integers that you are generating, we could have no multiple of 5. So it's possible that the 12 integers that we generate, none of them are 10, 15, or 20, right? We are randomly generating integers. It is possible that none of them are 10 or 15 or 20. In that case, the number of successes would be 0. It's possible that out of those 12 integers that we are generating, 1 is multiple of 5, or 2 are multiples of 5, 3 are multiples of 5, 4 are multiples of 5, because the number can come again as well, all the way up to 12. So x can have all of these possible values, right? Yeah, okay. So the number of times we're repeating something is what n represents here. So n is equal to 12. And this is the probability that we're looking for now. In the second part, they say, find the probability that x is between 3 and 5 inclusive. So we are looking for the probability that x is between 3 and 5. Do we have any formula in binomial distribution that gives us results for inequalities like this? No. What we have to do is we have to find these three probabilities. Probability of x being equal to 3. That's one possibility, right? Between 3 and 5 means it could be 3, or it could be 4, or it could be 5. These are the three possible cases that we can have, right? The value of x could be 3, it could be 4, it could be 5. Now, what's the probability of x being equal to 3? Let's write down the formula on the slide. The formula is NCR p raised to power r q raised to power n minus r. We know that the value of n is 12. We know that the probability of success is 0.2 and probability of failure therefore is 0.8. Now we just have to input values in the formula. In the first case, r is equal to 3. Remember, the formula is probability of x equals r equal to this. Let's just input values in the formula. You have to show this working. You can't write down the answer directly. That is not going to be acceptable. First of all, you say it's 12C3 for the first case into p, which is 0.2 raised to power 3 into 0.8 raised to power 12 minus 3, which is 9, plus probability of x equal to 4. That means 12C4 into 0.2 raised to power 4 into 0.8 raised to power 12 minus 4, which is 8, plus 12C5 into 0.2 raised to power 5 into 0.8 raised to power 12 minus 5, and that gives you 7. You calculate each of these probabilities, add them up together, and that will give you the final result. Now, after this point, if you write down the answer directly, that is acceptable as long as it's correct, but I would recommend that you show one more step. You calculate each of these probabilities separately and then write down the answer, because in case you end up getting the answer wrong, you will get more partial marks in that case if you were to write down those individual calculations first of all. If the answer is correct, then you will get away with it. But if for some reason you've done any calculation error, you will get more partial marks if you show the individual workings separately. So I would always recommend that you do this separately. And I think that's quicker as well, because you just have to write down the formula once. So we'll write it like this. Write this in brackets, 12C3. So 12C3. And then you have 0.2 raised to power 3. And then 0.8 raised to power 9. Okay, that's the first case. That is 0.2362. And that's the first case that you have. Plus, now you just edit this a bit. Replace 3 with 4 here. Replace this power with 4. And replace this power with 8. Okay, so the second number turns out to be 0.13288. And then the next one, you replace it with 5, 0.2 raised to power 5 into 0.8 raised to power 12 minus 5, which is 7. And that turns out to be 0.05315. You add all of these numbers up, and that will give you the result. You can see what that is. That's 0.422. That's your final answer. Okay, thank you. Make sense? Any questions on this? So calculations in this whole topic are not going to be a problem generally. It's going to be understanding the question correctly, right? That's going to be the tricky part. understanding what the question is actually saying and how to, and which method to use for that. Okay, now this is another very important type of problem that you will see in binomial distribution. Okay. Now, can I have raise of hands from those of you who have not done logs? How many of you are in A1s? How many of you are giving AS exams? Just to understand. How many of you have not done logs? Okay, so most of you here in the live class right now, you have done logs, all right. But okay, so let's do it that way first. So now they're saying she now produces n random integers between 7 and 21 inclusive. Find the least possible value of n if the probability that none of these integers is a multiple of 5 is less than 0.01. Again, the tricky part here is understanding what the examiner is trying to say here. Find the least possible value of n if the probability that none of these integers is a multiple of 5 is less than 0.01. How do we understand this statement? Let's break it down. Least value of n if the probability that none of these integers is a multiple of 5 is less than 0.5. What probability are they talking about? They're talking about this probability that none of these integers is a multiple of 5. Probability that none of these integers is a multiple of 5. That's the probability that they're talking about. Okay. Let's first of all find this probability, and then we'll do anything else after that. Let's first of all find this probability that none of these integers is a multiple of 5. Okay. That means we're looking for the probability of getting no successes, right? Of 0 successes. If none of them is a multiple of 5, that's 0 successes. Okay. So let's find this probability when we have 0 successes. Okay. How do we do that? Probability of getting 0 successes. That would be 12C0 into 0.2 raised to the power 0 into 0.8. Okay, I'm sorry. Let me just have a look at the question again. Okay, so she's producing n random integers now. So not 12 anymore. She's producing 12 random integers. Since we're looking for value of n is not known here. So we know that the probability of success is 0.2 again. Probability of failure is 0.8. But n is not 12. It is still a fixed number, but its value is not 12. Okay, it's n now. She's now producing n random integers. Okay. They're still between 7 and 21. So the probabilities of success and failure are still the same. They have not changed. So now this is going to be nc0 into 0.2 raised to power 0 into 0.8 raised to power n minus 0. Okay, now what does this evaluate to? What's nc0? Any number c0, I think we discussed that earlier. If not here, in paper 1, 5c0, 4c0, 10c0 in combinations. If we have 0 at the bottom, in fact, I think we did this in permutations and combinations. If you have 0 at the bottom, the result is always 1. Okay, no matter what the number on top is, this always is equal to 1. So that means nc0 is going to be 1. Okay, 0.2 raised to power 0, what about that? That's also going to be 1. And we're just left with 0.8 raised to power n. So this is 0.8 raised to power n essentially. Okay. So probability that we have no successes, that is equal to 0.8 raised to power n. Okay. Now, if this is 0.8 raised to power n, They are saying that this probability is less than 0.01. This probability is supposed to be less than 0.01. Okay. So this probability that we have calculated, they're saying this should be less than 0.01. And what we have to do is, we have to find the least possible value of n. So we have an inequality that looks like this now. It's 0.8 raised to power n less than 0.01. How do we solve this inequality? Now, those of you who know logs, I will show you how to do it using logs first of all. That's going to be quicker. But I'll show you an alternative. Those of you who are in AS and have not done logs yet, we will discuss another method for this as well without logs. But if you know logs, all you have to do is just take log on both sides. Any base, it doesn't matter. Generally, we use ln in A levels. So what we can do is we can take ln on both sides, and that gives us ln of 0.8 raised to power n. That's less than ln of 0.01. Okay, now using the power law, n comes down and it becomes n times ln of 0.8 less than ln of 0.01. And now we can divide this on the other side. But here you have to be careful. You have to be careful. Don't just divide it on the other side right away. If you remember your logs well, if you take log of a number that's less than 1, the result is negative. So ln of 0.8, it's a negative number. Don't divide it on the other side. For inequalities where you have logs, make it a habit. Before you divide it on the other side, first of all, evaluate this. Evaluate it and see what that turns out to be, so that you have it visible in front of you that this number is actually negative, in case it is negative, right? So in this case, it turns out to be minus 0.22314. Okay, and similarly on the right side, you have ln of 0.01, that is negative 4.6052. Now, when you divide this number on the other side, remember the inequality sign is going to change. The inequality sign is going to change, right? Because you're dividing by a negative number. So that gives you minus 4.6052 divided by minus 0.22314. So n is greater than this. You can see what that turns out to be. This divided by minus 0.22314. And that gives me 20.6. We were looking for the least possible value of n. What's the least possible value of n? The least possible value of n when that probability becomes less than 0.01 is going to be 21, since n is supposed to be an integer. The least integer that's greater than 20.6, that is 21. And that's what we get. So whenever you have inequalities and you use logs there, be careful about this. Evaluate logs before you divide them or multiply them on the other side. Because if the result is negative, then the inequality sign is going to change. So feel that might not, that might be a problem, because if you, so one of you is suggesting that we use log of 0.01 with base 0.8. You could do that, but again, you would be confused about the inequality sign in that case. So do we keep this less than? Do we make this greater than? Do we change the sign or not change the sign? So you need to understand whether the sign is going to change or not. One way is that you remember, if this number is less than 1, the sign is going to change, because log of numbers that are less than 1, they always turn out to be negative. So you change sign because of that. But I would say it's easier this way, so you don't have to remember anything. Take log on both sides, evaluate them first before you divide them on the other side. Okay? All right, that's one possibility. You can do it like this, and that will work. Now, those of you who are in AS and have not done logs, what do you do instead of this? Yes, you only have to do this in case of inequalities. Yes, in equations, it won't matter because there's no sign change in equations even when you multiply or divide by negative numbers, right? So equations are not affected. In inequalities, you have to be careful about this. Now, let's talk about an alternative for this. Those of you who are in AS and have not done logs yet, how could you do it without logs? You have reached this point already, 0.8 raised to power n, that's less than 0.01, right? Now you're looking for the least value of n that gives you a number that is less than 0.01. You can do it by trial and error as well. Okay, you can do it by trial and error as well. Now, how would that work? Just try some numbers on your calculator since n has to be an integer, right? So try, for instance, on your calculator 0.8 raised to power 5, assuming that we don't know what the answer is. Now we already know the answer, but let's assume that we don't know the answer, okay? So what you can do is you can say, let's evaluate 0.8 raised to power 5. Okay, that's 0.32. Is that less than 0.01? No, that's not less than 0.01. Let's try a bigger number. So 5 is not working. Let's try a bigger number. So when you're using the hit and trial method, it's a 3-mark question. You need to make sure that you show to the examiner how exactly you're getting to the answer. Okay, don't write that, just write down the final answer. So if you're trying 0.8 raised to power 5, for instance, write this down that, okay, you tried 0.8 raised to power 5, and it turned out to be 0.33, and that's not working. Okay, let's try another number. So let's try a bigger number, 0.8 raised to power 10. Let's see what that turns out to be. Okay, so that's smaller. That is 0.8 raised to power 10 is 0.107. Is that less than this? No, it's still not less than this. So that doesn't work. Okay, so let's try an even bigger number. So let's make it bigger than this. Okay, so let's try 0.8 raised to power 20. What do we get for that? 0.0115. Okay, so we are very close now. We want something that's less than 0.01, and we're getting 0.0115. It's still not less, but we are close to that point now. Okay, so now we can increase relatively slower now. So this was 20. Now let's try 21 and see what we get from that. So this is 0.0092. Is that less than 0.01? Yes, that is less than 0.01. So 20 did not work. 21 worked. That's the least possible value of n that makes this probability less than 0.01. So you say the least value of n is 21. And that's your final answer, 21. So you can do it using trial and error like this as well, as long as you show this working that I've shown on the side. Okay. Any problems with this? Any questions on this? No? Okay, now let's try a couple of more questions. Geometric distribution we will do tomorrow, okay? And tomorrow we will basically complete this topic. So we'll start with the concepts and then we'll do a number of questions on geometric as well. Let's do some more practice on binomial as today. So the next question is okay. 25 and 30. 30 is not binomial. Is it binomial? It doesn't look like it. What's the problem with 30?
द नंबर जो नंबर वाले क्वेश्चन होते हैं जिनके अंदर उनको बनाना पड़ता है और इनके सम्स होते हैं, सम करके ये आएगा और सब्ट्रैक्ट करके ये आएगा, तो ये सारे क्वेश्चन हो ही नहीं रहे थे, समझ नहीं आता कैसे करना है।
Okay, so let's keep it for the end of today's class. Let's do 25 first, and then we do the Sudoku question. That's one that I really want to do because that's an important one, the last part of this in particular. Okay, what I'll do is I'll start with 22 first, and then we do 25 and then 30. These three questions, and then we end, okay? So I'll start with this one, question number 22 first of all, and then 25. That's the second one that I will be doing. And then finally, we end with 30. Okay, these three questions. Okay, now this is a very important one. Question number 22. It basically covers another type of problem that you will get, that you will see in binomial distribution, and also sometimes in normal distribution later on, that you have one distribution inside another distribution. So you have one binomial distribution, and inside that you have another binomial distribution. Okay. Now let's discuss this to understand that concept. It's one part of this question. We will have a look at that. Question 37, part 4. Is that binomial? 37, part 4. No, it cannot be binomial because she's choosing two digits at random without replacement. So when she has already chosen one digit, then the probability next time is going to change, right? So when the probability changes, then it's not binomial anymore. Okay. So no, it's not binomial. You have to do it using simple probability concepts. Make a tree diagram and use that. Okay, let's have a look at this. Question number 22. Question 22 from the worksheet. It says, the probability that Sue completes a Sudoku puzzle correctly is 0.75. Sue completes n Sudoku puzzles. Find the least value of n for which the probability that she completes all n puzzles correctly is less than 0.06. Now, it's very similar to the last one that we did. I'll do this quickly as well. Again, focus on what probability we are talking about first. Okay, otherwise this whole statement is going to be quite confusing for you. Focus on this part. What probability are they talking about? Probability that she completes all n puzzles correctly. Okay, that's the probability that we're talking about. Okay. Probability that she completes one puzzle correctly is 0.75, and she's attempting n puzzles in total. Assuming that the probability remains the same every time, right? That's what they're saying. For any puzzle, the probability is this, and there's repetition, and we know that the total number of times it's repeating is n. The total number of times, the total number of repetitions is also fixed. That's n. This is binomial distribution. There are two possibilities. She can either solve the puzzle correctly or not solve the puzzle correctly. So success and failure, and their probabilities are remaining constant. Okay, so all the conditions for binomial, they are being met. So this is binomial distribution with p equal to 0.75 and q equal to 0.25. Let's write that down. So it's a binomial distribution. N is unknown. P is 0.75 and q is equal to 0.25. Okay. Probability that she completes all n puzzles correctly. Let's just focus on this part first of all. Probability of getting n successes. What's the formula? The formula for binomial is NCR p raised to power r q raised to power n minus r. We want how many successes? N successes. So we say probability that x is equal to n what's that going to be? Let's input values in this. NCN into P, which is 0.75 raised to power n, into Q, which would be 0.25, right? Q is just 1 minus P, 1 minus 0.75, so it turns out to be 0.25 raised to power n minus this, which is n. Now, what is NCN? Again, if both the numbers are the same, 6C6, 5C5, 10C10, 15C15, it always evaluates to 1. So NCN is 1. Okay, and then you have 0.75 raised to power n. And this raised to power 0, this is also 1. So 0.25 raised to power 0, right? So this simplifies to 0.75 raised to power n. So this is the probability that they're talking about. Probability of getting n successes. Probability of getting n successes. What is that equal to? That's 0.75 raised to power n. They are saying that this probability should be less than 0.06. So we put this number less than 0.06. And now we have to solve this inequality. Again, we can use both of those methods that we discussed. Either use logs or the hidden trial method. If we use logs, we take log on both sides, ln of 0.75 raised to power n, that is less than ln of 0.06. Again, evaluate the log first before dividing it on the other side, because if it is negative, then the inequality sign would have to change. Let's evaluate them and see what they turn out to be. Ln of 0.75, that is minus 0.2877, that is less than ln of 0.06, which is minus 2.813. And then when it divides on the other side, the inequality sign would reverse. And we get n greater than 9.78. And the least value of n that we were looking for, that turns out to be 10. Okay? So n has to be greater than 9.78. What's the least integer greater than 9.78? That is 10. Using hidden trial again, you can just try some numbers. So try, for instance, 0.75 raised to power 5. That will give you some value. That would not work. 0.75 raised to power 10. That will give you some value. Just actually do that process. So if you had to do it using hidden trial, how would you go about doing it? You would say, okay, let's try some power. Let's try 5 first. That turns out to be 0.75 raised to power 5, which is 0.237. Okay, and that we want the number to be less than 0.06. Is this less than 0.06? It's not. So the criteria is 0.75 raised to power n. It has to be less than 0.06, right? That was the inequality. So 5 is not working. Okay, let's try a bigger number. Let's try 10 and see what that gives us. Okay, so that's giving me 0.056. Is that less than 0.06? Yes, that is less than 0.06. But does that confirm that this is the first number at which it is less than 0.06? No, because I've not tried 9. So I have to try 9 as well now, just to see if that's also less than 0.06. We want the first number, the first value of n for which the result is less than 0.06. Let's try 9 now and see what 9 gives me. 9 is giving me 0.075. Okay, so this is not working. This is not working. This is working. So 10 is the first number at which the probability becomes less than 0.06. So the least value of n therefore is 10, and we can write down that answer. Okay, so if you're doing hidden trial, this is what you would have to do in that case. All right, if you don't know logs, if you're an AS, That's the method that you can use. Okay, good. Now let's move on to the next part. Okay, now Sue attempts 14 Sudoku puzzles every month. The number that she completes successfully is denoted by X. So now we are given that she is solving 14 puzzles. X is the number of puzzles that she solves correctly. X is the number of successes. Find the value of X that has the highest probability. Okay, now think about it. She's solving 14 puzzles in total. So it is still a binomial distribution because we have either a success or a failure. We're repeating something 14 times in total. And then what was the other possibility? And the other condition, the probability has to remain constant. That's also remaining constant, right? 0.75, 0.25, they will remain constant. We have to find the value of X that has the highest probability. And we are given that we can assume that this value is one of the two values closest to the mean of X. Okay. She's solving 14 puzzles in total every month. How many successes can she have? X, the number of successes could take a value of 0, 1, 2, 3, 4, all the way up to 14. So out of 14 puzzles that she attempts, she can either get none correct, or 1 correct, or 2 correct, or 3 correct, all the way up to 14. These are the possible values of 14 that we can have, values of X that we can have, okay? All the way from 0 to 14. Now they're saying, which of these values of X has the highest probability? Which of these values of X has the highest probability? Now, how do you do that? One idea could be to find the probability for each one of them. Find the probability for X equal to 0, X equal to 1, X equal to 2, X equal to 3, all the way up to 14. That will be 15 calculations in total. Too much work for just 3 marks. They've given you a hint. And the hint is that the value of X that you're looking for is one of the two values closest to the mean of X. So if you can find the mean of X, first of all, then you can identify, okay, it's going to be one of these two values after that. And you won't have to find all of these probabilities, okay? So let's find the mean of X, first of all. What's the mean of X? It's a binomial distribution. It's a binomial distribution. What's the mean for a binomial distribution? What's the expected value of mean or mean of a binomial distribution? It's n times p, right? N times p. You can call it expected value, you can call it mean, it's n times p. N is 14, probability of success is 0.75, and that will give you some result, that's 10.5. Okay, that's the value that we get. Remember, it's a binomial distribution with n equal to 14, p equal to 0.75, and q equal to 0.8. Okay. Now, 10.5 is the mean. They said the value that has the highest probability is one of the two values that's closest to the mean value. Which two values are closest to the mean? 10 and 11, right? 10.5 is the mean. One value is 10, that's close to it, and the other value is 11. So one of these is going to have the highest probability. Okay, I'm sorry, this was 0.25. One of these values is going to have the highest probability. So what we do for that, for this now is, we find the probabilities for these two outcomes. Probability when X is equal to 10 and probability when X is equal to 11. Whichever of these is bigger, we say this number has the highest probability. Okay, X equals 10. What's this probability going to be? 14C10 times 0.75 raised to power 10 into 0.25 raised to power 14 minus 10, that's 4. and that will give you some number. Can you please do this calculation and tell me what this is? 14C11 into 0.75 raised to power 11 into 0.25 raised to power 14 minus 11, that's 3, and that will give you some number as well. What do we get from this? Okay, 0.220 and 0.240. These are the two probabilities that we're getting. Which one is higher? This one is higher. So this is the biggest probability. Now, what did they ask for? They asked us for the value of x that has the highest probability. They did not ask us for the probability. They wanted us to write down the value of x that has this highest probability. It's x equals 11. The most probable case is that she solves 11 puzzles correctly out of 14 puzzles. That has the highest probability amongst all these possible values of x. These are 15 possible values, right? 0, 1, 2, 3, all the way up to 14. 11 has the highest probability. It's 0.24. That's the highest of all the possible probabilities that you would have amongst those 15 numbers. Okay, and that's what we were looking for. That's the second part. Now, the third part is why I wanted to do this question in particular. It says, find the probability that in exactly 3 of the next 5 months, Sue completes more than 11 puzzles correctly. Now, what does that even mean? So we were talking about 1 month earlier. In 1 month, she was attempting 14 puzzles. Okay. Now we're talking about 5 months, that in the next 5 months, what's the probability that in exactly 3 of them, she solves more than 11 puzzles correctly? Now, that's quite complicated, right? How do we think about this? So I'll give you 30 seconds to think about it while I answer this question. Yeah, so how do we handle some very complicated questions like this, and every single part you have something new coming up? Practice. Just do a lot of practice so that you don't end up feeling that every question has something new. So once you have done enough practice, you will find in the exam that 70 to 80% of the paper will be something that you would have seen before, as in would have seen very similar questions to that earlier. And if you do practice the right way, not by rote learning, by understanding the concepts for everything, then the remaining 20%, 25% of the paper, that will be solved using those concepts that you've learned along the way while you were practicing. If you were practicing the right way, understanding at every single step why you are doing what you're doing, then you would be able to crack those remaining 20-25% of the questions as well. But it comes with practice. You have to do a lot of practice, making sure that you understand the concepts well, first of all, and then for S1, for instance, for most of the topics, you need to have attempted at least 25-30 questions while you are covering the concepts, while you're covering the topic, and then the last 4 or 5 years of yearly past papers, as many of them as you can in this time now. Start from the most recent ones, 2024, and then go backwards as far back as you can go. And when you do them the right way, understanding for every single thing that you're doing, why you are doing it, then those remaining problems, which are going to be different from the questions that you've seen, those concepts that you have, those strong concepts that you have, they will help you understand or figure out those different questions in the exam as well. If you're rote learning, those remaining questions will be very hard. So they will only be possible when you've understood the concepts very well. Okay, so we will do this when we do the yearly past papers in a few days, when we start the yearly past papers, when we do the whole paper in a go. Hopefully that will provide you enough practice for that as well. So let's have a look at the next one now. Yes, okay. Part 3, it says find the probability that in exactly 3 of the next 5 months, Sue completes more than 11 puzzles correctly. Now, what is it that we're looking for? Look at the big picture first. We are talking about 5 months. In 5 months, we want that in 3 of them, she solves more than 11 puzzles correctly. Okay, let's write that down here. Part 3. We're talking about 5 months. In every single month, she is solving 14 puzzles. We're talking about 5 months. Something is repeating, right? It's a binomial distribution with n equal to 5. So it's a binomial. Distribution with the value of n being equal to 5. Okay. And what we're looking for is the probability of getting 3 successes. Probability of getting 3 successes. And how is the success defined? Success is that she completes more than 11 puzzles. This is the criteria for success. You will call 1 month successful if you can, 1 month will be successful for her if she solved more than 11 puzzles correctly in that month. Okay. That's the criteria for success. All right. So in this binomial distribution, success is defined as in 1 month, she solves more than 11 puzzles correctly. That's the criteria for success. Now the question is, how do you find this probability? What's the probability of success that she solves more than 11 puzzles correctly? This is another binomial distribution. So we have 2 binomial distributions. One is for the number of months that months are being repeated, right? 1, 2, 3, 4, 5. There are 5 months in total. And in each month, then, she's attempting 14 puzzles in total. So that's another binomial distribution. So this is, you can say this is this is the outer binomial distribution. I can say this is the first binomial distribution. Inside this, you have another binomial distribution, and that is the earlier one that we were already talking about. In which in every month, she was solving 14 puzzles. In this binomial distribution, this 14 represented the number of puzzles. So she was solving 14 puzzles. And the criteria for success here was, success was defined as solving 1 puzzle correctly. That was the criteria for success. What was the probability of success here? 0.75. What was the probability of failure here? 0.25. The probability of success of this binomial distribution is going to come from the other binomial distribution. Okay? The probability of success of this first binomial distribution, it will come from this other binomial distribution. So we will first have to find probability of getting more than 11 successes from the second binomial distribution. How do we do that? Probability of x being greater than 11. What are the possibilities? X can either be equal to 12 or it can be equal to 13 or it can be equal to 14. These are the three possibilities that we've got. X could be 12, 13, or 14. We find the probability for each one of these cases separately, and then we add them up together and see what that turns out to be. 14C12 into 0.75 raised to power 12 into 0.25 raised to power 14 minus 12, which is 2, plus 14C13 into 0.75 raised to power 13 into 0.25 raised to power 1, plus 14C14 into 0.75 raised to power 14 into 0.25 raised to power 0. What's this number? Has anyone done this? What is this resulting? .281, we want more accuracy because this is not the final answer. We have to use this in another calculation now. So we want more accuracy. Okay, 2811. Okay, all right. So this turns out to be 0.2811. That's the probability that in 1 month, she solves more than 11 puzzles. Now, this acts as the probability of success of the second binomial now. That's 0.2811. Then the probability of failure would be 0.7189. That's the probability of failure for the second binomial. And in this second binomial, now we're looking for having how many successes? 3 successes out of 5. So now in the second binomial, we've got n equal to 5, p equal to this, and q equal to this. And now we find the probability of getting 3 successes. That's 5C3. We've got 5 months in total. Out of them, we want 3 successes. 5C3 into 0.2811 raised to power 3 into 0.7189 raised to power 5 minus 3, which is 2. And that should give you the result. You can see what that turns out to be. What's this number? 0.115 to 3 significant figures. This is now our final answer, so we can round this off to 3 significant 0.115. Thank you. So that's the result that we get. Okay, 0.115. Make sense? Now, this will happen in more difficult questions in binomial, geometric, and normal distributions. It's a common type of problem that will come, and it's the more complicated one, in which what happens is you have a binomial distribution. Like in this case, you have a binomial distribution. And to find the probability of success of this distribution, you have to use another distribution. Okay. Now, in this case, the other distribution, the second distribution, was a binomial as well. As we will see later in the next topics, topic, and also in geometric distributions, sometimes that second distribution could be geometric. That second distribution could be normal. Okay, so you might have to find this probability of success using geometric distribution sometimes, or using normal distribution sometimes as well. So the outer distribution would be binomial, but then for finding that probability of success, you may have to use binomial or geometric or normal. Okay, so that is what can happen sometimes as well. All right, that was question number 22. Now, for the other 2 questions, I'll try to be relatively quicker now. Hopefully we can do that. Okay, question number 30. I want to get done with them with these today. If you think it's too late for you, I'll be uploading the recording right away as well. So in case you miss the other 2 questions, you can catch up using the recordings, because tomorrow we want to do geometric distribution then. All right. Okay. What was the next one? 25? Okay, let's have a look at this now. Question number 25 from the worksheet. Let's try this. A factory makes a large number of ropes. A factory makes a large number of ropes with lengths either 3 meters or 5 meters. There are 4 times as many ropes of length 3 meters as there are ropes of length 5 meters. One rope is chosen at random. Find the expectation and variance of its length. Okay, now whenever they say something is happening a large number of times, and they don't specify what large means in that case, you assume that it's very large. It's like approaching infinity. It's extremely large. Okay. Now there are 2 types of ropes that we've got. They're either 3 meters or 5 meters. The 3-meter ropes are 4 times as many as compared to the 5-meter ropes. So we can say the ratio is, you can write that down here, 3 meter to 5 meter. Which one is bigger? 4 times as many ropes of 3 meters. Okay, so this is, if this is 4, then this is 1. That's the ratio. Okay. So if you were to choose one rope randomly, probability of it being a 3-meter rope, what would that be? That would be 4 over 5, right? The total is 5. 4 out of 5 are 3-meter ropes, and 1 out of 5 are 5-meter ropes. These are the probabilities for both types. We need to find the expectation, that means the expected value and variance of the lengths. Expected value and variance. That is what we're looking for. Now, how do we do that? Do we know the total number of ropes? Don't assume that it's 5. Okay? The total number is not 5. It's a large number. Okay? It's a large number. Now, given that it's a large number, we can say, for instance, if there were 5,000 ropes, then this would be 4,000, and this would be 5,000. This would be 1,000, right? If this was 40,000, then this would be what? 10,000, right? That could be a large number. Okay. Just let me think about it. Okay. I think it will be much easier to just make a table for this because we've got 3, we've got 5, and we've got the probabilities. Okay. So for 1, we can just make a table. So we have only 2 possible outcomes. We can just list down their possible outcomes. So it will become fairly straightforward that way because in the first case, we're not repeating anything. So I was just thinking that this is going to be binomial, where it's not really required as such because we don't have repetition anywhere. So we have 2 possible values of x. So we can denote the length by x. Okay. If we denote length by x, then x can have 2 possible values. It can either be 3 or it can be 5. What's the probability of 3 that we have written down here? That's 4/5. And the probability of failure, that is 1/5. So this is 4/5 and this is 1/5. And all you have to do is just apply the formulas. The expected value, that is given by sigma xp, and the variance is given by sigma x square p minus expected value of x whole square. Okay, so the first part is not binomial as such. You can just do it directly like this. Let's see what that turns out to be. 3 into 4/5. Let's add another row to the table and see what that gives you. X times p. 3 into 4/5, that is 12/5. And this is 1. What's sigma xp? Sigma xp turns out to be 17/5, which simplifies to 3.4. That's the expected value. That's 3.4. And what about variance then? Just input values here as well. Add another row to the table, x square p. 3 squared times probability, that's 9 into 4/5. That would be 36/5. And then 25/5, that's 5. Sigma x square p, what does that result in? 61/5. So 61/5 minus 3.4 whole squared. What do we get from this? What's this number? 0.64. 0.64? Okay, so that's 0.64. That's the result that we get. Okay, so that's the mean and that's the variance. So that's just simple discrete random variables. It's not any of the distributions that we have done. Now the second part says 2 ropes. Yes, Ibrahim.
मैंने भी लाइक इस तरह टेबल बना लिया था, उसके अंदर एक्स का मैंने 3 मीटर रख दिया था, 5 मीटर रख दिया था, लेकिन मुझे ये नहीं समझ आ रहा कि आपने जब मल्टीप्लाई किया है तो ये क्यों किया है? वो तो लाइक एक ऑर्डर में होते थे ना, जब एक्स होता था वो तो एक नंबर होता था, बट दिस इज
लेंथ इज अ नंबर, राइट?
लेकिन ये तो रोप है ना, एक मतलब एक 3 मीटर की, एक 4 मीटर की.
But we're talking about length. Length is a variable that represents some number, right? X से हम length denote कर रहे हैं, right? X represents length. So that's a number. So in earlier problems as well, whenever we made a table, X used to be some number, right? It does not have to be all possible numbers in the order. For example, here as well, you don't have 5 here, you don't have 9 here. It could be some specific numbers as well. It's a discrete distribution. So you can have any specific numbers and that's okay. Part 2 says 2 ropes are chosen at random. Find the probability that they have different lengths. Okay, now how do we do that? Now we're choosing 2 ropes at random. Okay. Find the probability that they have different lengths. Now here we would need that idea that, okay, the first time you take out a rope, the probability of the rope being a 3 meter rope is 4/5. And the probability of it being a 5 meter rope, that's 1/5. What about the second time you take out a rope? what would the probability be in that case? Remember, the total number is not 5. The total number is not 5. The total number of ropes is not 5. It's a large number of ropes. Now, even when you are taking ropes without replacement, if it's a large number, if it's a very large number, think of something very close to infinity. So for example, so I can't give an example of a number that's very close to infinity, but let's take a relatively large number just to understand this idea. Let's say the total number of ropes was 5 million. Okay. Now, in that ratio, the number of 3-meter ropes, that would be 4 million. So the probability of this would be 0.8 from this, right? Or 4/5. If you were to take out one rope, if you were to take out one rope of 3 meters from this, what would happen? The next time, the probability of getting a 3-meter rope would reduce to 3,999,999 divided by 4,999,999, right? The total number would reduce by 1, and the number of 3-meter ropes would also reduce by 1. Both the numerator and the denominator, they're going to reduce by 1. Now, what happens when you do that? 3,999,999 divided by 4,999,999. What do you get? That's 0.799999 and so on. If I were to choose larger numbers, it would just continue like this, 0.799999. If it was infinite, it would be the same as 0.8. If you take out 1 from infinite, what's that? That's still infinite. Okay. So you see the probability is not changing by much. 0.7, 0.799999, and then infinitely many nines. And that also rounds off to 0.8. So when you have a large number of ropes like this, and you're taking out one rope after the other, the probability is still not going to change. The change is so negligible that we can say that it remains constant. Okay. So the probability that you take a 3-meter rope the first time, that's 4/5. The second time as well, it is going to be the same. It's not going to change, even though this is without replacement. Okay, so they're saying they have not said without replacement. Whenever they don't say anything, you assume that this is without replacement. Okay, so if it was with replacement, they would always tell you in the question. So if they don't say anything, it's understood that this is without replacement. So when they're taking out one rope, they're not putting it back. But even though it is without replacement, since it's a large number of ropes, because of that, the probability remains constant. It does not change. Okay, it is without replacement. It's not with replacement. So don't just look at don't look at the marking scheme and think that since the probability is not changing, it's with replacement. No, it is without replacement. The reason the probability would not change would be because they're saying that it's a large number of ropes. So probability remains constant. Okay, so the probability of taking out 2 different length ropes, then what does that turn out to be? There are 2 possible cases. One possibility is that the first rope that you're taking out, that's a 3-meter rope, and then the second one is a 5-meter rope. And the other possibility is that the first one is a 5-meter rope, and then the second one is a 3-meter rope. You add up these two cases, or you just evaluate one of them and multiply that by 2. The first case would be for a 3-meter rope, the probability is 4/5, and then 1/5 for the 5-meter. And then you add to that the other case, 1/5 into 4/5. That will be 4/25 plus 4/25. That's 8/25. That's the probability that you get in the second case. And that simplifies to 0. That in decimals is 0.32. That's the second part. Okay. Let's look at the next one now. That was part 2. Part 3 says 3 ropes are now chosen at random. Find the probability that the total length is 11 meters. Okay, so now what we have to do is we have to consider the possible cases that can make the total length 11 meters. Okay, how can the total length be 11? The total length can be 11 if we have 1, 3, another 3, and a 5. Is there any other possibility? 3, no, there's no other possibility. You need 2 3s and 1 5, okay? But they can change order, right? So you can have 3 3 5. You can have 3 5 3. And you can have 5 3 3. There are 3 cases. You find the probability for one of them, just multiply that by 3, and that will give you the result. So this is 4/5 into 4/5 into 1/5. And that will be the same for all of them. Just multiply it by 3, and that will give you the result. You can see what that is. Yeah, so you can also do 3 factorial over 2 factorial. That's the number of arrangements that you can have for this, right? 3 factorial divided by 2 factorial, because 2 of them are identical. So that's basically 3, and that will give you the result. You can see what that is. What's this number? 16 over 125 times 3, that's 48 over 125, which simplifies to 0.384. 0.384. That's the probability in the last case. Okay. All right. One last question, and then we end. It's been a very long session. Tomorrow we do a geometric distribution, inshallah. Okay. And then we start normal distribution after that. This was 25. Let's do this one last one. That's question number 30. Let's try this. Okay, question number 30 from the worksheet. Let's have a look at this now. It says a fair tetrahedral die has 4 triangular faces numbered 1, 2, 3, and 4. The score when this die is thrown is the number on the face that the die lands on. This die is thrown 3 times. The random variable x is the sum of the 3 scores. Show that the probability that x is equal to 9 is 10 over 64. Okay, a fair die, that means the probabilities of all outcomes are the same. It's a tetrahedral die. Tetrahedral means it has 4 sides, 1, 2, 3, 4. They have specified that as well. It has 4 faces. Okay, score is the number that you that the dice lands on. Okay, it's thrown 3 times. X is the sum of the 3 scores that you get. Show that the probability that x is equal to 9 is 10 over 64. Now, can we make a table for this? We can't, because there are 3 events that are happening. We are throwing 3 dice, right? So we can't make a 3-dimensional table. We could think of a tree diagram, but tree diagram, in the first step, it would have 4 branches, and then 4 times 4, 16. And then 16 times 4, 64 branches. That will be very big, right? For 3 marks. Again, that's a lot of work. So making a tree diagram or making a table for this, it's not going to be very straightforward. So what we do is we just think of it directly. How can we get a sum of 9? Let's think about that. From these 4 numbers, 1, 2, 3, 4. Okay, now do this in order. all right? So that you don't miss out any possibility. If the first number is 1, if the first dice lands on 1, what should be the other numbers? They can be 4 and 4. That's one possible case. All right. Okay. What else? If the first is 2, then with 2, what could be the other two numbers? With 2, you can have 3 and 4. And with 2, you can also have 4 and 3. And that's it. There are no other possibilities. Okay. Then with 3 being the first number, what are the possibilities? The second number could be 1 and then 4. That would not work. The second number cannot be 1 because if it's 1, the third number can be maximum 4 and the sum would not be 9 in that case. So second number cannot be 1. If the second number is 2, with 2 you can have the last number 4. That's one possibility. And if the second number is 3, then the last could be 3 as well. And then if the second is 4, the last could be 2. And then with 4, the second can be 1, and then you can have 4. And then you can have 4, 2, 3, 4, 3, 2, and 4, 4, 1. You can also understand the pattern. Once you've done 2 of them, you notice that with 3, you have 3 cases. With 4, you have 4 cases. So there are 10 cases in total. Once you've listed down these cases, that's it. You have 10 cases that satisfy the condition. How many total cases would you have? You're throwing 3 dice. For one of them, you have 4 possibilities. For 2 of them, 4 times 4, 16 possibilities. For three of them, 4 times 4 times 4, that's 64 possibilities. So the total number of possible outcomes is 64. Out of them, 10 satisfy the condition. So what's the probability that we were looking for? It's 10 out of 4 times 4 times 4. Show how you're calculating 64, right? It's given in the question. You have to show you're working. It's 10 over 64. So in order to get full marks in this, you would have to clearly show these cases that justifies this numerator being 10, that you have 10 cases like this. And in the denominator, you have to clearly show that you're multiplying 4 3 times or 4 cubed. Okay, that's how you can do it. No, you can't do it directly. Instead of listing down the only other possibilities that you think of it in your head, but you have to show your working. So you have to list down the cases. Now, yes, you can list down the cases a bit more efficiently. You can say with 1, you have 4 cases. Yeah, so another possible way of doing this could be that you list down the cases like this. You say you can have a sum of 9 with, but I think that's actually going to take longer if you use permutations. That, for example, if you do 1 4 4, then you say that, okay, there are 3 possible arrangements for this. And then you do 2 3 4. There are 6 possible cases for this. Yeah, so that's not actually going to be longer. So that's another possibility, that you could list down the cases a different way. You could say one possibility is that you have 1 4 and 4, these 3 numbers. Now they can be arranged in different ways, right? They can come in different orders. And how many different orders can they come? 3 factorial over 2 factorial. So that's 3 cases. And then another possible set of numbers that could give you a sum of 9 could be 2 3 and 4. And how many different orders can these numbers come? They can come in 3 factorial ways. So that's 6. So that's 9 cases in total. What other possibility is there? With 3, you could have 3 3 and 3. And how many orders can this come? That's just 3. That's just 1. So this gives you 1. So that's 10 in total. And so there are 10 cases that satisfy the condition. And then in the denominator, you would have 64 like before. So that could be another way of listing down the cases, but you still have to list down the cases, but you could do that listing a bit more efficiently if you do it like this. All right. Any problems with this? Yes, 𝗲𝗽𝗀, you were saying something?
Yes, sir. I was saying about I was about to say about this.
Sorry?
Sir, I was about to talk about this method that you
Oh,
talked about.
okay, all right. Okay. So yeah, so you can list down the outcomes this way as well. That's another possibility, but you have to list down. Okay, you can't do it directly without that. Okay, part 2. Now copy and complete the distribution table for x. Now, whatever you did for x equal to 9, you have to do that for the rest of the numbers. Now, how would you do this? Let's write this down. First of all, this is 10/64. How do we complete this table now? We have 5 probabilities to calculate, left to calculate. Start from the extreme ones first. Okay, they will be quicker. So a sum of 12. When is a sum of 12 possible? When all the numbers are 4, right? So for 12, all the numbers have to be 4s. So what's the probability for that? It's one outcome out of how many? 64. This is 1/64. How can you get a sum of 11? A sum of 11 is possible with 3, 4, and 4. How many arrangements of this can you do? 3 factorial over 2 factorial, right? This can come in 3 factorial over 2 factorial ways. That's 3 out of how many? 64. So this would be 3/64. Okay, let's try 10 or 5. So again, you should be able to look out for a pattern here as well. It looks like it's following some kind of pattern. This is 1/64. It's 1/64 here. This is 3/64. This is also 3/64. Okay, let's just confirm what's happening with the rest of them. Let's try 5. How can you get 5? 5 is possible with 1, 1, and 3. And 5 is possible with 1, 2, and 2. And that's it, right? And how many ways can you arrange this? 3 factorial over 2 factorial. That's 3 ways. And how many ways can you arrange this? 3 factorial over 2 factorial. That's 3 ways. That's 6 in total. So this would be 6/64. Okay. Then what about 6? 6 is possible with 1, 1, 4, 1, 2, 3, 1, 4, 1 would just be an arrangement of that. 1, 3 would be, okay. So with 2, 2, 2, that's another possibility. Is there anything else? With 2, you need a maximum of 2 there, or you have a 1. Yeah. So the first one is 3 factorial over 2 factorial. That is 3 again. The second one is 3 factorial, which is 6. And the last one is just 1. And that gives you 10, which is 10 out of 64. Okay, so now that's kind of confirming that pattern as well. You see, this was 3/64. This was 3/64. This is 10/64. This is also 10/64. So that means this one here should be 6/64. And then this one here should be 12/64. And you can confirm this as well by adding all of these up. If they add up to 1, that means that's correct. 1 plus 3 plus 6 plus 10 plus 12 plus 12 plus 10 plus 6 plus 3 plus 1. That's 64 divided by 64. That's 1. So that's your table. That's part 2. That completes the table. All right. That was the second part. Now it says event R is that the sum of the 3 scores is 9. Event S is that the product of the 3 scores is 16. Determine whether events R and S are independent. Showing your working. Okay. Remember the condition for independent events? Condition for independent events? The condition was if 2 events are independent, if 2 events A and B are independent, probability of A intersection B, that should equal probability of A times probability of B. Right? That's the condition for 2 events being independent. What 2 events are we talking about? There's event R, and that is that the sum of the 3 scores is 9. Do we know that probability? That's 10/64. So probability of R is 10/64. Okay. Then there's another event that the product of the 3 scores is 16. Let's find that probability as well. Product of the 3 scores is 16. Let's see what this is. How can you get a product of 16? What are the factors of 16? 1, 2, 4, 8, 16. Okay. Now, of course, we can't have numbers greater than 4. So we have to use 1, 2, and 4, right? There are no other possibilities. How can we get a product that is 16? Let's list down the possible outcomes. With 1, we could have 4 and 4. That's one possible case. How many arrangements of this can be there? 3 factorial over 2 factorial. That's 3 cases in total. Okay, what else? With 1, we can't have any other possibility. With 2, we could have 2 and 4. How many possible arrangements are there for this? 3 factorial over 2 factorial. That's also 3. And then that's it, right? 4, 4, 1. That's already considered. Yes, yeah, so there's 6 possible cases. Probability of S is therefore 6/64. That's the probability of S. So we have the probability of R, that's 10/64. We have the probability of S, that is 6/64. And now we have to find the probability of their intersection. Intersection is when both of these things are happening together. How can you find the intersection? Let's look at these cases. This case is the sum also 9. Remember, this is when the sum is 9. And this is when the product is 16. Now, what's common in them? In the product being 16, one case is 2, 2, 4. Is the sum 9 here? No, it's not 9. Another case is 1, 4, 4. Is the sum 9 here as well? Yes, the sum is 9 here as well. These 3 cases are what are common between R and S, right? When you have 1, 4, 4 or any other arrangement of this, 4, 1, 4 or 4, 4, 1, in these 3 cases, the product is 16 and the sum is 9. Both conditions are satisfied in these 3 cases. So we can say probability of R intersection S, when both of those things are happening together, that is 3/64. And now we can check if that condition is met or not. Probability of R intersection S, let's figure out if that is equal to probability of R into probability of S. Let's see if these are equal or not. R intersection S probability, that's 3/64. Probability of R is 10/64, and probability of S is 6/64. Let's simplify this and see what we get. On the right side, we have 60 divided by 64 times 64, and that simplifies to 15/1024. On the left side, we have 3/64. They are not equal to each other. If they're not equal to each other, that means they are not independent. If they turn out to be equal, then we would say they're independent. If they're not equal, we say they are not independent. And that's what we had to do in this part. These two events are not independent. Okay. Any problems? Any questions? No? Okay, so that was a very long session. Let's end this here. Tomorrow we do geometric distribution and its questions, and inshallah. The yearly past papers test sessions, they will also start from Monday, by the way. The next week, therefore, is going to be a bit hectic because there will be an overlap between these classes and the past paper sessions, as an overlap in the sense that on the same day, we will be doing both these classes and then the yearly past papers. So it's going to be a few hectic days next week, just 3 days. And then once we're done with the syllabus, it will only be past papers. So P1, P3, as I posted on the group as well, is going to be from 6 to 8, and M1, S1 from 8:20 to 9:50. Okay, and these classes will finish next week then, inshallah. And then the week after that, we're going to get back to normal as far as the number of hours of studying math is concerned in a particular day. Next week, 3 days in particular next week, they will be a bit hectic. So be ready for that. Make sure that you're practicing regularly. In order to reduce those 3 days, I was just thinking we could do a class on Sunday as well. So we don't have an overlap of 3 days next week and we reduce it to just 2 days. How many of you are up for a Sunday class, by the way? So what I'll do is I'll post it on the group and let's see how people respond to that idea. R is for Thursday. So in that table that I made for listing down the number of days, for showing you the number of days on which we'll be doing each paper, R stands for Thursday, right? So that's a convention. Since T is already taken for Tuesday, we can't use T again for Thursday. We generally use R for Thursday. Okay. Yeah. So in order to reduce that hectic routine for 3 days to 2 days, we could have a class this Sunday. I'll leave a poll on the WhatsApp group and see how everyone responds to that. If the majority is up for it, we might have a class on Sunday. That way, we would only have 2 days next week on which we would have both the past paper session and this session. All right. Okay, but that's it for today. Tomorrow we do geometric distribution and its questions, and on Saturday we start normal distribution then. Allah Hafiz.